to one of these screens so you can see where we're going. And it looks like, yeah, there's not really any comments. I guess I'll just go ahead and switch both screens over.
Yeah, sorry.
Yeah, so if there are issues with exercise 5, questions about stuff from lesson 5, we're going to give you the opportunity to talk to us about those at the break perhaps, because we're not seeing anything here in the poll.
Yeah, so there was the optional exercise. Maybe if you're brave, did you try it? Nobody admits, maybe yes. So that's a topic that we will cover today. So don't worry, maybe that was a test that is it easy just to pick up these things from the web by Googling. Grouping data is one of those things that takes a bit more time to grasp, so we'll cover that today, and we can then provide a model answer to that exercise 5, problem 4, or then maybe go through it next week, but I wouldn't now spend time on that before we have actually learned those approaches.
Yeah. So, okay, I guess what we can do now is take a look at where we're at. So we're on to lesson number 6. We've only got one more week left in our Geo-Python part of the course. And here is what we're going to talk about today. Basically, we're going to continue with our data analysis using pandas. So building on what we encountered last week, we're going to cover some new topics here, and basically like a part 2 of the data processing in pandas lesson. So we saw some introductory stuff last time, how to read data files and how to do some basic processing of the data files, looking for values that are missing and removing them, things like that. And the big sort of step today is we're going to jump to doing things like taking data that is related to time and grouping it in various ways. So if we have measurements of, for instance, temperature data, like we'll work with in the lesson today, maybe they're taken several times an hour, but perhaps what we're interested in is knowing like what's the average temperature for the day or the average temperature for a month or whatever. So that's what we're going to get into. And I will say maybe 2 other things at this stage. The most of the time for today will be on this pandas lesson, then we'll squeeze in some stuff at the end about interpreting error messages, and we do have a good coding practice part of the lesson today. So if we run out of time, it's not a big deal because those things you can read through them. The emphasis is certainly on the pandas part of the lesson for what we're going to talk about. But the other thing I wanted to mention is that we made the decision to change this lesson about 4 o'clock yesterday afternoon. So there could be some bumps in the road, so to speak. But I wanted to say, acknowledge Volko because she put in a lot of work to make sure that the lesson was tested and working. And I think it's a pretty fun and interesting lesson. So hopefully you guys think the same. And hopefully any sort of issues we encounter are minor in nature.
And practice problem solving skills in a YouTube live video. So that's always nice.
Yeah. So so we can, I think, just jump here to our lesson for the week. Hopefully you have opened up a CSC notebook, or you have your own notebooks open on your own computer. And I'm going to do the same thing here, jump from the web page over to my notebooks. There, I think, is still some kind of transition happening right now. So some of you may not see the lesson 6 lesson materials.
So maybe let's pause here for a minute and check that people have the materials in there. Solution 1, if you don't see lesson 6 folder in there, destroy the instance, relaunch it, and we'll go around. We can then manually clone the materials there. Sorry for the trouble. Yeah. But yeah, maybe we'll spend a few moments to check that you have
you can just check here in the notebooks directory. If you don't see L6, then don't panic, but maybe just raise your hand so that we can see who doesn't have the lesson materials, and we can kind of come around and help people. For those who are waiting to be helped, there is one thing we can try. So if you go to File, New, and open a terminal window, you'll get something like this. And if you type cd notebooks /notebooks and hit enter, you can type ls to then see the files that are there. And it may work for you to just type git space pull, which should pull down the latest changes. If that doesn't fix things, then let Vocal or Lotto know. But if you do git pull, I don't know if I can maybe make this a bit bigger. Let's see. View. Maybe I'll just do it like this. Maybe that's a bit easier to see. So yeah, if you're in a terminal, you type cd notebooks /notebooks to get into the notebooks directory, and then git space pull. It may give you some message saying that there's conflicting files and things like that, and if that's the case, then we'll deal with that. But does this work for anyone who didn't have the lesson 6 materials? Does anybody have it working at git pull? Didn't work. So it's conflicting changes or something like that, that it says something will be overwritten or, yeah, okay. All right.
Check out the changes and then kind of remove the previous whatever edits it's complaining about, and then
Yeah.
that's the only way.
Yeah, so it's most likely the fact that you've got local changes, and that we have updated some of the files on the notebooks Git repository after the lessons. So I guess, why don't I try to simulate this while we just have a second here. So if I go to lesson 5, you don't need to do this part because you've already got changes to your files, but I'm just going to make some little change here, like this. So I'm going to change this file and save it. And actually, this will probably work for me. Yeah, that works for me because this is already updated. If you have made modifications, you'll see that there's a list of files up here. Like when you type git status, you should see a list of modified files. If you then just type git checkout -- and then you can copy paste the name of the file, that will give you the updated, or that will basically restore the file back to its original version. If you've got a list of like 10 files, you have to do this several times. But if you check out that file, you should then be able to type git pull once all of the changes that are not staged for commit have been fixed. It's most likely lessons 4 and 5 that are going to cause problems because we made changes to them after you had already started working. So yeah, maybe we'll pause here for a second. I can come around and try to help those who are still stuck with various issues. be dealing with like a bit larger data sets, then Finder will probably crash. Yeah, so check out, okay, yeah. So there should be a space here between the two dashes and the L5. Let me just see what it says. Let's just try, if you try git pull, it'll tell us these files are going to be overwritten. So if you do git checkout, since you're already in the notebook directory, you only need like this L5 piece. And so we'll copy that. That will basically restore the file back to its original version when you start the lesson. So if you do the same thing for the other files as well, you can type that. If you then type git pull, it should then be able to update. It's a weird thing that we've updated the files on the Git repository, and it doesn't want to. It doesn't know how to handle it. Like maybe you have your files, there's an updated file. Yeah. Okay. So yeah. Okay. So let's try doing git. Let's try git pull just to see which files it might pull. Okay, so it says you've got L4 module.ipynd file. Yeah. Okay. So if you type git space checkout space, oops, sorry. Space checkout. Yeah, space. Actually, hold on, it may have. Why don't you try git pull now? Actually, maybe just refer to all the files at the same time. Yeah, so you can do git space checkout space, and then the file name there, but just without the notebook in front of it, so like L4/modules. Yeah, like that. That basically restores it to the unmodified state. Now you can do git pull, and it should work. If you do the same thing, yeah. So if you type, should it be him? Oh, there. Yeah. So that should be basically exactly the same thing. Yeah. Checkout space L4/modules. Capital L. It looks like maybe you're not in the notebook directory, so and then you can press up twice to get to the Okay, very good. No worries. I think
Mostly, yeah. Maybe you can follow with your
Okay, so technical issue set number 1 has mostly been handled. So everybody should now have this notebook for lesson 6 directory, and we're going to be in the advanced data processing with Pandas lesson. So you can go ahead and double click to open that one. I'm going to get the file tab out of the way so that we can focus on what we're doing here and maybe just make this a little bit smaller. Okay, so we've dealt with the first thing, which was getting these lesson 6 files available for you. Before we move on to getting you the data, which will be our second big step, we'll just talk for a second here about what we're doing. So I came across an article, I don't know, a few weeks back, I think, about how global temperatures in April of this past year were the second warmest ever recorded. And as it turns out in the article, they specifically mention here that 13 locations in Finland had their record warmest April. So 13 of the weather stations here recorded the warmest ever April temperatures in 2019. So we thought that might be kind of a fun thing to explore because we have access to the climate data. Why don't we pull some of this data and see for ourselves whether this, whether we see any indications that April 2019 was the warmest on record. So there's a nice little map here, and you can see, of course, in the colors that we're sitting up here somewhere in the kind of darkest red area in terms of temperature anomalies, meaning it's warmer than average by something like more than 4 degrees Celsius. So it's not sort of an insignificant difference in temperature from this past April. In order to do this kind of data analysis step, we're going to need to do a few things to our data. We're first going to pull the data down, but we're going to need to do some renaming of columns. We're going to need to go through and process the data in different ways. So converting temperatures from Fahrenheit to Celsius, because once again, we're getting data from the US NOAA organization. So we need to convert temperatures to things that are familiar. And then we're going to have probably the big step for today, this data aggregation step, where we take these more frequently than hourly, I think, temperature observations and condense them down to monthly values so that we can compare April 2019 to April from every other year in the data that we have. And in some of these cases, I think we're going back as far as like 1901. So there's quite a bit of data that we're going to be processing. And you'll see from the size of the data files that we've got in all something like a gigabyte of data that we can churn through. Certainly more than you would want to manipulate in something like Microsoft Excel. So we're going to kind of get to see the reason that we're learning how to use these tools like Python programming in our lesson today. So as mentioned, the input data we have were downloaded from the NOAA. There are either 15 or 4 data files that you're going to be working with. Unfortunately, on the CSC Notebooks platform, we can't put all 15 files in memory on the cloud machines because they have a pretty small disk space available, and we'll use it all up if we try to unzip the file with all the data files. So we're going to take 4 of those for those of you on the CSC Notebooks. If you're using your own personal machine, you can go ahead and download all 15. There's instructions for how to do this on the course page, but I'm going to walk you through how to do this for the CSC system because we've got a CSC notebook open here and we can do this stuff ourselves.
I'll walk around, so just raise your hand to get everybody started with the lesson, so important to get the data downloaded.
Yeah. So I guess for many of you, you probably already have a terminal window open. If not, you can go up to the file, new, and then go to terminal to open the terminal window. So I'll do that. I'm actually going to take this terminal window and drag it down to the bottom half of the window here so I can see the notebook that we're working with, as well as the terminal window. If you've got your terminal window open, most likely you're already in the notebooks subdirectory because we were just doing this git pull thing. So the instructions will vary a little bit person to person, and if you get lost, let one of us know. But since I'm just opened a fresh new terminal, in order to get into the lesson 6 directory, I'm going to have to type cd notebooks/notebooks/L6. If you're already in the notebooks directory, you could just type cdl6. So I'll just do that same thing. So cd is just changing directories, and of course it just depends where you are. If you change into the L6 directory and there's no error messages or anything like that, when you type ls, you should see files for this week's exercise that are there, like the advanced data processing with Pandas notebook, debugging errors, some other notebooks that look like that, and a couple directories that are there. If you're in this location, when you type ls, then things are good and you can continue. If not, again, let us know. But what we're going to do next is to download the data. We'll use a tool called wget. It's just a simple command line tool for downloading files off of a web page. There's lots of different possibilities to do this, but we'll use wget because it's already installed and available. And I'm just going to copy paste this command here. So this wget and then this website, you can copy paste that into the terminal and hit enter, and you should start seeing some stuff about how the files are being downloaded, maybe some kind of status bar or something like that. It runs pretty quickly, at least for me. You can see it only took a second there to download the files. But that should basically pull down our data file. You can type ls again if you'd like, and you should now see this Finland weather data csc.tar.gz. If you're working on your personal computer with your own Jupyter notebook or Jupyter Lab installation, I suggest you scroll down to the next section for the file name you should download there. I don't really think too many people are in that group, but if you are, you can go ahead and download the files that are listed there. It's basically the same file name with full instead of CSC. So that has 15 data files instead of the 4 that we have in our CSC version of the data. Once you've downloaded this, we're going to use another fun command here called tar, and we're going to give it some flags. So we're going to give it xzvf. I'm not going to bother explaining what that means, but it's what you have to type in order to get the tar command to work. And then we can type in our data file name. I'm just going to type capital F-I-N and then hit the tab key, because tab will automatically complete the name of the file for me, so I don't have to type in this Finland-weather-data-csc blah blah blah. When you type this command and run it, you should see a few little warning messages here about ignoring stuff. This is because I created the archive on a Mac, and on the Linux machines that we're using and the CSC, it's got a slightly different tar command. It doesn't recognize some files. You could ignore the warning messages, that's not a big deal. The important thing is if you type ls space data, that you should now see there's a directory that's called data, and inside there are these data files. We don't really know anything about them yet, but there's 4 files that start with some number sequence.txt, and then there's a few other files in there that are actually metadata files. So these are files that describe the data that is in our 4 data files that we have to analyze for today. Is anybody having trouble with this part? All right, well, that's surprising, I suppose. Not that I'm questioning you, but more that like the instructions actually seem to have been accurate enough to give us the data files. So if you've got the data files, now we're basically ready to proceed with the lesson. And what will happen is I'm going to kind of introduce you to a few things, and then I'm going to tag out, and Volko will take over when we get into the heavy-duty Pandas stuff, because I'm still a Pandas newbie. So just to note, there are instructions here about how to use Jupyter and to do this analysis on your own personal machine if you're running Jupyter on your machine and not using the CSC Notebooks system. You can read through those if that is your case. And again, for the Binder people, we don't suggest using Binder for this exercise or for this lesson, because I don't actually know whether there's enough space to analyze the data or to download the files. So if you're not using the CSC notebooks, now would be a good time to switch over to doing that. Okay, so a few things about the data before we move on. There are some metadata files here that are linked on the in the notebook for this week. I'm going to go ahead and move my terminal window back up here to the tab bar so that I can have this whole thing visible. So what you'll find in here is there are some text files. If you click on one of them, you can see, perhaps I just clicked on the top one, so this is the list of stations. If you click on that, it might look kind of ugly like mine does here. But if you go to View and then turn off the Wrap Words option, that will make it a little bit easier to read. Essentially, the line length is too long to be displayed, so it wraps. But here you can see these are the different stations that we have data for. So there are 15 in total. I think we're only going to be using 4, and I don't remember exactly which 4 we have. I think we have Turku and Tampere-Pirkkala, and maybe Helsinki-Vantaa as well, and one more. Could be Oulu, I don't recall exactly, but you can find, for instance, here in this metadata, information about the different stations we have, which includes this identification number. That's the number that's out in the front of the text file names for the data that we'll be analyzing. Of course, the name of the station, the country where it's located, and then the longitude, latitude, and elevation for the station. So there's some information there that could be interesting, perhaps. We can also see things about the number of observations at each station. So in the second file there, you could click and you can see, for instance, here for Sodankylä, for 1917, each one of the columns that follows after this is the number of observations that were recorded that month. And so this gives you some sense of the volume of data that we're dealing with. So 93 observations from January of 1917, and as you might imagine, the volume of data generally increases as we get closer and closer to the present day, such that by 2019 we now have 744 observations per month in January. So that means we're going to have 744 lines of data for the month of January in our data file. And as you can imagine, if you start adding all these numbers up, it means our data files are pretty long. I think it's something like at least 4 million lines total, but could be even more than that. I don't exactly recall. And lastly, there's a description of the data, which basically just tells you what all the column headings stand for, what's recorded in each of those. You can, of course, read through that as well, but I'm not going to spend any time on this. It's mostly just if you're interested to know what these different columns mean. For many of the stations, they don't have this information. This is a sort of standard data format that's used by NOAA. So some stations will have things like the record of the cloud cover and things like that. Other stations won't. Pretty much all of them record temperature and precipitation, maybe relative humidity, but there's many other things that can be recorded that aren't always available. So for the files that we have, this looks kind of ugly. It's unfortunately, I don't know a nice way in the Jupyter notebooks to not make it wrap the text in a little thing like what we have here. But this is the header, or the top 5, I guess, top 5 lines of our data file, just to give you a sense of what we're looking at. So there's station names and some other things here. We've got a date, this year, month, day, hour, min format for the date. There's a direction for wind, wind speed, gust, and a variety of other things, including temperature. That's going to be the thing that's perhaps most interesting to us for today. So that's our data file. It looks sort of familiar because I think we used more or less the same data format last week, with the exception that last week we had comma-separated values, and today we have values that are sort of fixed width. So that means there's a variable number of spaces between the columns, which also means we need to read the data file in a little bit differently because we don't have a comma. We have spaces, and it's not just 1. It could be 1, 3, 5. There's different numbers of spaces between the columns and between the observations, which makes this a little bit harder to read in this data file. To get us started here, we can go ahead and import pandas as PD, like we always do, using the shorthand there, and I'll just run that cell to import pandas as PD. Should be no problems with that. The data file we're going to be working with here is this 029440.txt, and this is for the Tampere-Pirkkala observation station. And as mentioned, when we read the data file in, we need to handle a couple things here. We're not going to make you go through the sort of cumbersome process of typing this part in, but you should see underneath the blue box here about the data structure a cell where we have a file path defined, data slash, and then the file name. And then there's a pandas read CSV function call there with our file path, so that's basically the name of the file we're going to read. There's the NA values thing that should look familiar from last week. This will just convert any number of up to 5 or 6 asterisks to NaN values, so not a number values, basically missing data. And then there's a new guy here, this delim whitespace equals true. This is a handy little thing in pandas because it basically allows us to avoid the kind of tricky part of reading a file with multiple spaces by just saying that the delimiter, or the thing between the columns, is whitespace. Doesn't matter how many white spaces, it's just anything that's blank will be interpreted as something that should be breaking the columns apart or separating them. So this delim whitespace equals true thing will allow us to, instead of specifying the sep like we did last week, allow us to read with variable amount of spaces between our columns. There is also the possibility of doing this with sep as noted in the blue box above. You can use this sort of somewhat strange notation, but that will also do similar things, although I've read something saying that this is a little bit less robust, so the suggestion is to use delim whitespace equals true. With all that said, you can now basically just select the cell and then do Shift Enter to read in the data file. You will get this warning message here. I think everybody will get that warning message, more or less just saying that there are some mixed data type columns. We're not going to deal with those, so don't worry about the warning message. All this is doing is just reading in our file, and if we then take our data file, it's been read in as data, and do data.head, you should be able to see what the data file looks like. You can also print data.head if you want, but I always like this nice formatting that Jupyter notebooks do. And so you can get a sense here that we've got observations for this weather station starting in 1906. Remember, the first 4 values here for the date column are the year, and some other information here. But you can see there's a ton of missing data, lots of NaN values. And because of that, and because there's 5 rows by 33 columns, we don't necessarily want to deal with all of that data. If we do our data.columns command, you can see here all of the different columns that we have, and we're not really concerned with so many of these. So we're going to read the data file a second time. And this time we're going to use one of the other nice features that you can use with the pandas read CSV file function, and that is to specify this thing called use calls, which says that when we read the data file in, we only want to use certain columns out of that data file. And here you can find the list of columns that we want. So we want the USAF, that's the station ID, the year, MODA, her, column, that's the date, DIR and SPD, that's the wind direction and speed, gust, which we won't actually be using, temp, and then max and min, so the maximum temperature for that day and the minimum temperature for that day. Or maybe it's for that observation period, rather. So again, you can just do Shift Enter on this cell down there. The only difference is that now we're just going to take these, 7 or 8 columns instead of all 33. And now when we do the data.head, you see still our station identification, but now many fewer columns, and we have basically only the data that we're interested in working with. So sometimes when you read a data file in, you're going to have lots of things you don't care about, and this is a nice way to kind of strip out that data right away and not even bother reading it in, because if you read in some really big data file, of course you can always drop columns later, but it may take a long time to read the data file in, and there's no point in storing that data to begin with. In some cases, your computer might run out of memory if you try to read too large of a file, so that's also a reason to think about using this use calls parameter to only get certain columns in. I think I can continue with this renaming columns part, and then we'll switch over when we get to the next step here. But when we type in data.columns, of course, that gives us back the columns that we have in our data frame. So again, you saw the ones that we've already seen here. And the thing is that sometimes these column names are perhaps useful for the data format that's being stored, but maybe not intuitive. Like some of them, like this your moda blah 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 thing, might be nicer to store just as time. And SPD we can convert to speed, just so that we don't have to worry about like these shorthand versions of some of the column names. So to do that, we're going to introduce something new called a dictionary. It's a certain new data type, something we haven't encountered previously. And typically it's used for storing things where there's a key and then a value associated with that key. So it is sort of like a dictionary, that there's a word and then there's a definition that's associated with that word. The thing that's handy about this is that we can create a dictionary to allow us to rename our columns in one kind of quick single line command. So we can create this dictionary, and I think it's called new names. And the thing to watch out for creating dictionaries is that we are going to use this curly brace now. So it's the one with the little sort of, I don't know, notch in the side of it. And then inside here, we're going to list a series of keys and values that are separated by a colon. So we're going to have, for instance, year, moda, and then that would be the first thing, then a colon, and then what we want to rename that as, which is just simply time. Then you can have this semicolon character, no, comma, sorry. And then after that, we can basically list the next one. So again, SPD, and we want SPD to be associated with speed in quotation marks. And finally, we can take Gus and make that be gust. So that'll create our dictionary where we have our key and then the value associated with it. So here we'll take this column and convert it to time, SPD to speed, gust to gust. And then we can basically just print out what we have in our new names dictionary. So print new underscore names. And while we're at it, we might as well go ahead and print out the type of new names, just so that you can indeed see that new names is a type dict for dictionary. Let's see. So here we have created our dictionary. We print out the values and it looks like what we typed in. That's good. And then we can see, of course, the class is a dictionary. Now, with this, we have the possibility to use one of the Pandas functions to rename the columns. So we'll say here now that our data equals data.rename. And then in parentheses here, we're going to say columns equals new underscore names, the name of our dictionary. And what this is going to do then is just do a substitution. Any place it finds this year moda thing, it's going to replace that with time in the columns. Of course, that's only going to happen really once because it's just the headings. But if we run this and then print out the data.columns that we had before, now we can see that we have now time, speed, and gust instead of the values that we had previously. Any issues with this?
I still have the old names here.
Okay. Did you type data equals data.rename
Yeah.
like this part?
And then after that, rerun the data.columns.
Oh. It's just there was a space missing.
Ah, okay. All right. So yeah, hopefully that works. And if so, that brings us here to our first task for you for the day. And that is to rename a couple other columns. So we have a column called temp that we would like for you to rename as temp_F because those are Fahrenheit temperatures. And as you can perhaps glean, we're going to also be calculating some temperatures in Celsius. So we want to avoid the confusion. And also that this USAF should be renamed as station number. So using what we just saw, you can basically follow the steps that are here in the comments in the cell underneath this task and go ahead and rename two of the other columns. And we'll give you a few minutes maybe to do that and then check in and continue on with the lesson.
In the start, so that's fine.
But yeah, I can do this content.
Yeah, I can jump in.
Take over. Yeah. Yeah. So how many of you have managed to rename the other two columns? Maybe get just show of hands. Okay. I think it looks like we're making progress. Those of you who are still working, of course, can finish what you're doing, but I'll at the same time provide this sort of solution for the task here. So again, we'll create another dictionary like we did before called new names. And I'll use the curly braces to do that. In this case, we want to convert our USAF column to be station underscore number. I guess I'll keep it in capital letters. And we want to convert our temp column to be temp underscore F. So that's our dictionary that we're going to create that will allow us to convert these two column names. Then of course we can do data equals data dot rename columns equals new names. So same thing that we did previously, pretty much exactly with a different different dictionary in this case. And then we can print out data.head or just type data.head here to check and see that our column names have been renamed as we expected. So if I run that now, I can see that the USAF has been replaced by station number. That looks good. And that temp has been replaced by temp F. Also looks good. And I think hopefully you have found the same thing when you did this. Any questions about renaming columns or any issues about this? Okay. If not, I think we'll switch over to Woko, who will, as she said, warm up a little bit with some data frame properties and then get into some heavier duty pandas stuff.
All right, yeah, let's see how we'll do with time, but we'll, probably cover most of the important stuff. You have now read in the data, renamed some columns, and we're kind of ready to move forwards with the data analysis. So to remind, we're trying to detect the warmest April on record in Finland across first using this one station, and then to see if that holds across all the stations in Finland. So are these headlines true actually based on data? Just to refresh our memory from last week, very basic Panda stuff always when reading in the data. So let's check a bit what we have. For example, data.shape gives us the number of rows and columns. Now that we only read some of the columns, we have 8 of them, and then you can see that we have 75,000 plus rows. So I don't know if that's big data, but it's quite a big data file as such already. So maybe a word of warning: if your kernel dies at some point, don't panic. We tried to increase the memory on the blueprints, but we are dealing already with quite a big data file, so some of the processing steps might take a while. Not to mention when we will run the thing for all the files. And then let's once more check how the data looks like. Oops. Top rows, data.head. Dave already discussed this, but indeed here the observations already start quite far back, so that's cool. It's a good idea always to also, or sometimes to check the tail, just to see that we don't have any empty lines, and so it looks fine. And from here we can see that the latest observation is from last week actually. So I think, when did we download this data? Yesterday or the day before? So we have very fresh observations. Of course, we won't be needing these lines of data if you're only focusing on data from all the Aprils in record. All right, data types of the columns, D types, as we learned last week. So we have station number and time as integers. So the time column is important as we want to extract Aprils, and then the kind of wind and temperature variables are floating points. We won't be needing speed and gust as Dave said. For the Finnish speakers, gust is puuska or puuskainen tuuli, gusty winds. Last year we had this case of detecting Kiira storm from 2017 based on gusty winds, but now we're focusing on the hot Aprils. Then data.describe method, as we learned last week, provides us some descriptive statistics across the whole data. So over 100 years of data here summarized. But what we eventually want to do is to zoom into all the Aprils, take average of temperatures in each April, and then see what are the top warmest Aprils in record. So for that we need to do a bit of data processing to split the data and aggregate the data. Okay, I think everybody is with me. So the main learning goals in terms of Pandas functionalities are to we have already learned to define our own functions, do some calculation using our own functions, but now we'll combine functions and pandas. There are a few tricks for doing that. So how can we use our own functions with data stored in the Pandas data frame. That's kind of one big goal. And then the second one is data aggregation, so grouping data, condensing data based on the values. But let's start with the functions. And here we're not introducing anything new. We have a familiar Fahrenheit to Celsius function here predefined and with a pretty nice doc string in place describing what it does. So here we have, it takes an input value as Fahrenheit, converts it to Celsius and returns the Celsius value as floating point. So this should be familiar to us already from 2 weeks back. And also last week what we did was to convert the values in Pandas just using this basic arithmetics one-line calculations to do the conversion. As we are now only doing kind of this simple, using a very simple function, let me find the correct spot. We only need one line of code and we'll start from there. So the kind of goal would be to add a column, temp C. So temp Celsius, the NOAA data is in Fahrenheit, as you can read from the metadata file. So we want to have a new column temp C and calculate the Fahrenheit values using this function. So actually it's not more complicated than calling the function. Far to Celsius, and then we can give as a parameter a Pandas data series, so one column of the data, temp F, zoop, Celsius, did I? That's true. Yeah, I didn't notice that. Kiitos, Lotta. Okay, so if you don't get any errors, something has happened. And just to check what we got, can type in data temp C, and not to print out all the rows, I can just check the head of that one column. Or then I could check the head of the whole data frame actually to see what happened. So in principle, even if we had this function that kind of deals with individual floating point values, if we give a Pandas series to that function, Python is able to kind of apply the function on each value in the data series. It returns a series and then we can assign that into a new column in Pandas. Like this. But if we would be, for example, if we would want to combine this with a conditional statement, for example, so apply this function for each row that meet a condition, we would have to do this in a bit different way. So I'll now here show a few other ways of how you can then apply functions to Pandas. You might be needing those in the exercises. Sometimes you can also just define your function, use it directly, create a new column with one line of code. Okay, but any questions about this? So here comes the for loop. So here we now learn how to combine also for loops and Pandas data frames. As you remember, a data frame is a two-dimensional data structure with rows and columns. And the data frame object has this method iterRows that we can use for iterating over the rows. So for each row, do something. We have the syntax should be there, so you don't have to type this in. And when we are iterating
the rows, we actually get information of the index of the row, so row 0, 1, 2, 3, 4, and then the actual values of the row. So as columns in Pandas data frames are series, so are the rows. So one row of data is actually one Pandas series. And if we would then do for index and row in data iter rows, print index, and then print one value from one row, and run this, we would get the value for the first row. I don't know, did we, Dave, introduce break on week 3 with for loops? Okay, well, just to make the point, if I would remove this break, you don't need to do it, but I'll just show here. If I just loop through all the rows in the data frame, I print index and then one value from that row. So I actually get quite a few outputs. I won't even go and scroll down because I don't want this to die. As you remember, we have 75 plus 1,000 rows in our data set. So it goes through the data frame, prints out index ranging from 0 to then 75,000 something. So when developing for loops and when developing, for example, some processes with Pandas data frames, sorry, might be that this was a very bad idea because now it's still printing everything. Tested this with a bit smaller data frame, but maybe this makes the point that when dealing with relatively large data files, you sometimes don't want to actually print out all the values, and that's why we have the break in there. Okay, I'll just try to kill this process. Sorry about the delay. Yep. Okay, there it goes. So I think if I just rewrite the break there, I hope not many of you ended up in that situation, but these things, when we start working with real data, these things happen. You end up with not enough memory or the kernel dying. So let's see what happens then next. This kind of iterating over the rows of a Pandas data frame is something you need to probably work hands-on with before you deeply understand what's going on, but that's the basic idea. We iter rows and we get the index and then the row values. Okay, and then combining that with the function, we could do the same. We did this one-liner of applying the function for each row of the data frame or for each Fahrenheit value. So this is the same thing done in a bit more complicated way. I will now run this and it will probably take, I would say, up to a minute to run, so you can also try that. It shouldn't freeze, and while we wait for it to run, I might use that time to explain what's happening. So here I'm creating just a name for the column, so I can refer to that column name in multiple places in this code that follows. And then I create a new empty column for the temp Celsius. This is sometimes a good idea to think about the output you want to create, then maybe create an empty variable or empty column for the outputs that you will generate, and then finally do the calculations. Then we iterate over the data frame for index and row in data iter rows. Then we kind of use this temporary, well, not temporary variable, but this help variable Celsius inside the for loop. We calculate Fahrenheit to Celsius, and we give row temp Fahrenheit as the parameter, and we can see then now, maybe I can show here. So now in the memory I should have the last row of the data. So I'll show here, you don't have to type this in if you don't want to. So likewise with iterating over lists, I have now here the last round of iterations in memory, so the values for the last row in our data frame from last week. And there the temp Fahrenheit was 37. So then in this for loop, I would give the temp Fahrenheit from one row to the function, calculate the Celsius, and then using this data at accessor, for that row index, new column, replacing the value. Yeah. So then finally, after the for loop has gone through, I could check data.tail, for example. So now on the final row, there was the temp F37. It has been converted to temp Celsius. Okay. But this is basically the same thing that we already did when applying the function for each row. So for each row, take the Fahrenheit value, use the function, store the output to the new column. All right. Do you have some questions about this?
Yeah, I have one.
Mm-hmm.
I'm not sure what's the difference between this process and the
In terms of the output it produces, there's no difference. But we are showing this as well because then, for example, if you would want to add an if statement, so if for some reason we would want to do the conversion only for Fahrenheit values greater than 30, then you could easily put it in here. And this is also maybe just conceptually helps you to understand what happens when you apply things for each row in a data frame. So there are situations when you need to use this for loop. Sometimes you can only use this one-liner when you apply the function. Yeah. Okay. So it's a code for doing the same thing. All right. And then there was this, I have a little note about this data at or data lock. So also this data.lock index new column would produce the exactly same amount. So as you remember, we have this, last week we learned how to access rows and columns. So for example, if I have data at row 0, column temp F, I'll just show you to make the point. So using this at, I can access one value. I can also update the value using the at. And with lock, the point is to then access several columns, several rows with a condition. But those materials are then in last week's lesson. Okay, but this you might want to come back to when doing the exercises, for example, or sometimes in the future when applying things on Pandas rows. All right, and just to confirm what we did, so now we have, using two different approaches, converted temperatures in Fahrenheit to temperatures in Celsius. So it's not that complicated at the end. Still, to keep things not so simple, so there is a third way of combining functions and Pandas data frames. I'll just show that quickly as well. So this is again the same thing. We would want to update the column data temp C by calculating the Celsius values based on the Fahrenheit column. And in this case, the syntax would be Fahrenheit column from the data frame dot apply, then function name. Oops. let's see if I wrote everything correctly. And here I'm just re-updating the same column all over and over again. If I would check data.head, nothing changes, but this is another way of using your self-made or other types of existing functions in Pandas. And here you notice that we only call the function name without the parentheses. So in a way, kind of behind the scenes, it then gives each value in that series as a parameter to the function. Why we're introducing these different ways is performance. So if you would compare how long time it takes to do this pandas iter rows versus this apply, I think apply is, I don't remember how many times faster, but quite a lot faster in terms of execution time. Then again, sometimes, as I mentioned, if you would include if statements and other more complicated things, you might prioritize code readability and use the for loop instead of like a big long one-liner apply. Yep, but then you can see when doing the exercises which one of these approaches, either using the apply or the iter rows, or then using the function name and giving a column as a parameter, does the trick. Any questions about this? So there's different, if we would have a column with string values, we could apply some function on the string values. Here we're just demonstrating the same thing with the Fahrenheit to Celsius conversions.
Yeah, maybe just one thing to think for an example of why you would use the iter rows. I mean, Wolfo mentioned something like if you had to do something where you were doing an if statement, you could think about classifying temperatures. If we wanted to classify temperatures as like warm, hot, cold, whatever, we basically have to go through value by value and check the individual temperatures. I suppose you could probably come up with some clever way to not need to do that, but the sort of simplest way to do it for us at the stage we're at would be just to go kind of value by value, say, is this value above or below some threshold, and then assign some perhaps text label name for whether that temperature is warm, cold, whatever.
All right, so I guess I'll go through this parsing dates and then we can have a break, as we lost some time in the beginning. All right, so as I said, there's two big things, applying functions, so that was basically it. We'll practice more that in the exercises. Then finally, thinking about our task, so we should be able to, now that we have the Celsius temperatures, we should be able to take the average Celsius temperature for each month of April. And thinking about the data that we have the column that we renamed as time, which probably contains that information, but not yet in a very usable format. So if we check the column time, I'll again print only the head. Maybe let's take 10 first rows to check a bit more. So you remember there's the 4 first numbers represent the year. Then there's 2 digits for the month, day, hour, and minutes. So basically we would need the information of the month, which is here, but we also need to maintain the information about the year, because we want to have a separate average value for April 2019, April 2018, April 2017, and so on and so forth. So we should kind of cut out information of the month and the year from the time column, and then drop the information on the hourly level and on the daily level that we don't need in this task of looking at the warmest April on record. I'll just copy this here. Didn't do that. Command C, Command V, and check the tail. Just to remind about the last value. So as you probably could already observe, so the first first days, 1st of January 1906 has 3 observations there, but then when we come closer to present day, then we have even several observations per hour, so we have quite a lot of data that we want to then summarize. Okey-doke. Still, I just copied the name of the column in here and confirm that we are dealing with integers, and we can then continue based on that. So again, I'll give some options. There's 2 ways of approaching this problem of getting out the information about the month. And we'll first discuss about string slicing. We haven't done that too much before, but if we have a string object in Python, you can kind of think of it as a list. So you can take, for example, the 3 first elements in that character string and store those in a new variable. So here's one example of timestamp we have in the data. Just to demonstrate what is string slicing, and let's say we would have that. We already know how to convert data types, so we could have the date as a string object in memory, and then now again, if you think of it as a list, we can then start slicing. So based on the index in that object, we can take the first 0, 1, 2, 3, 4, 5 elements, and then the upper limit would be 6, which is not included in the slice. So using that logic, we would get October 2019 out of that string slice. Makes sense, right? In a similar way, if I would only want the month, I could do 0, 1, 2, 3, 4 is the start index. There I have the month. But in this case, we need, stay on page. Yeah. We need information of both the year and the month. So then we just need to do this in Pandas. So first, we want a new column. We can call it, for example, time string. And then based on the existing time values, we remember that they were integers. So there was this as type function zoop. What did I miss? Data. Yeah. The sleepiness index might be quite high. Anyway, so data series dot as type new data type converts our values to string. Zoop. Never mind that. Anyway, they are now character strings. I think what I could do is data.d types. So now you see that time string is an object, so character strings are objects basically. Then we can slice that information in time str data and store the output to a new column called, for example, I'll now call it year month. And as an input, we'll use this data time string column. And for doing the string slicing in Pandas, we need to use some Pandas series methods. So there's .str.slice, which does the same thing as we did with the string slicing and the brackets, but here the syntax is a bit different. So we give the start index and then stop index. In there. And then you can see that in this year month column, you have the needed information based on which we can then start grouping the data after the break. Yep. Maybe in the interest of time, I don't know, should we skip date time? We don't want to skip date time. Yeah. Okay, maybe let's first do this until the end. So who's with me at this stage? Yeah, okay. So this is quite intuitive. You have kind of bucket of words and you can slice them based on their position in that word. And now that we learned that, I'll again introduce an alternative way of doing the same thing. So Pandas and Python have this, or I guess it's NumPy datetime data type that we're dealing with, but there are more clever ways to deal with dates and times in Pandas. So there is this Pandas function 2, date time, that converts string characters into date time objects that then we can modify a bit in a more clever way. So I might as well do so that I'll show this and then we'll break for 15 minutes after that.
Can I maybe say one?
Yeah.
So one quick thing about this date time and the reason why it's actually something useful is if you think about things like years, months, days, they don't always like have the same number of days in a month, and you don't have like some obvious number. I mean, of course there's 24 hours in a day, but 24 hours doesn't necessarily always play nicely with things like when you have increasing, from the last day of one month to the next, or the last hour of one day to the next. You sort of take these sort of unusual jumps instead of going from like 99 to 100 like you would with regular numbers. If you put something in to this format that we're dealing with now, you can sometimes have somewhat odd data to deal with. So like when it comes to things like finding the last day in a month, this date time sort of format can be really useful because you can do things in like a single quick step. So yeah, there's a reason for this, and if we have time we can talk a little bit more about it at the end of the lesson.
Yeah, and also the curious thing here, it also, similarly as with the iter rows, this PD2 datetime is a bit slow with our 75,000 rows of data. So we could do so that once you typed it in, press play, and then let's break for 15 minutes. So let's continue 10 to 11. And then we can still discuss date times if you have burning questions. But I got my results here now. If I just print the head of that column, I can see that the data type is date time. All right. Does my mic work? At the back? No? Yes? No? Okay, maybe I don't have it on. Yeah, that's... How about now? No? No, now it works. Okay, so let's continue. I think we'll, yeah, yes. So a couple of general announcements. So I first of all go to Slack because there's a lot of good discussion going on. Second of all, if you went to Slack, you would know that the deadline for exercise 5 has been postponed because there was some issues with the CSC environment last week. So, and some of you might have gotten stuck because of that. So to allow everybody to learn from the exercises, the deadline is on Friday at 4 p.m. So you can still also take advantage of the exercise sessions this week as well. But of course, we recommend that you finish it in order to have enough time for exercise 6. Okay. Anything else? In general, there were some very good questions during the break regarding the for loops with iter rows and other things. So hopefully you'll then keep those questions in mind, ask here, ask on Slack, and then also ask at the exercise sessions. So we got so far that we have extracted information about the year and the month using string slicing, and now we are at the point where we managed to convert our time that was as a character string into a date time data type, which is a handy thing to use in the future. You might have noticed that running this cell also took some time, but it shouldn't kill the process. Is everybody at this stage? Pretty much, if you're following. Okay, so I have data frame with a new column date, which has then, it renders the dates in a bit different way. So year, month, day, hour, minute, second, I guess. And then we can extract the information we need from there. I'll just show it quickly in here. So now that we have a date time column, we can call data frame column name capital date dot dt. So this is kind of an accessor or an access method for dealing with date time objects in Pandas. And for example, we can call date.dt.year, and we can get the year for all these 75,000 rows. And then I'll go and copy paste that here. You can always combine these other Pandas functionalities we already learned. For example, to check how many years of data do we actually have. In this dataset, there seem to be 51 unique years. That might vary a bit according to the stations, because there might be some wars have happened and so on when there hasn't been any recordings of weather observations. Okay, I think in the interest of time, we'll just do this task together. So let's create 2 new columns called, so first we want a column called year, and another column called month for future purposes. And let's store based on the date time column, which is data, sorry, my Mac keyboard tactics are not so smooth. Command C. So based on the date column dt year into the year column, and then same syntax but with dt month. So if you're wondering what all can you do with these datetime objects, there we have this link to the documentation of this DT accessor library, I don't know. So there's many things you can do with datetimes, but now you should have 2 new columns with information on the year, information on the month, because next step would be to get rid of all the other months except for April. So now we have 1 column based on which we can do the selection. All right, so finally, some actual, well, still data processing, but going towards data analysis. So data aggregation. In Finnish, that would be aggregointi, which is a kind of weird word, but in principle, you have many rows of data and you want to condense it. Now we have observations per hour, so 75 rows of data, and in the output we would want on each row to be a mean value for each month of April in the data. So considerably less rows in the output. And for this, we'll use a Pandas functionality for grouping data. So we will call a function called dataframe.groupBy, and then we need to think about which information we are grouping by. So it's the month information, of course, but combining month with the year, because if we would combine with month of April, so month number 4, everything, so then we would get an average across all the 51 Aprils in the dataset, but we want each April for each year to have its own average value. So that's why we have this combined year and month column in the data at the moment. Okay, to get forwards, let's just again once more check the data. We did that already, but we indeed have so many rows, and we should have all this information here now. We have this year month column, and we have even year and month in separate columns. Here's a bit like 2 different approaches on how to do that, either with the string slicing or then using the datetime variables. And indeed, the output should have only 1 row per month. So let's do that. When grouping data using Pandas, you usually do something like this, that you create an object or a variable for a grouped object. We'll see soon what's that about. And we can just call it grouped. You can also come up with a nicer name. And then we do data.groupBy. And then we need to tell the function based on which column we want to group the data.
Grouped. You're missing R. In the
Grouped.
variable name.
Well, grouped. Does it mean something? I don't know. Anyway. Okay, just even if we are kind of running out of time, I want to show the documentation here. So now we are introducing yet another function. This is quite zoomed out, but anyway, you can open it yourself. So there's different parameters we could use, but almost always you only need the by parameter. So by which column should I group the data? So the data, the column we want to group by is then, we could do year month, year month. Let's hope this goes through smoothly. It does. Ignore that note because the column names don't match at this point. So now that we told Pandas to group the data based on year month, we have this kind of a bit mysterious grouped data frame group by object, which has a length of 601. And now there's a little task for you to think that what does this 601 mean? Why do we have a length of 601 in the grouped object? You can think on your own or discuss with your friend. I don't know. Should I go? Here maybe it doesn't show for the video, but just to answer the question now, so we have the 75,000 rows in our input data, and then we group by year and month. So we have this column with information on year and month. So then the output, if we group by that, with this example would be with these values, then the output would have 2 rows. So in our case, we have this 75,000 rows from 51 years. So I don't know if somebody could calculate 51 times 12. Is that 601? Might be close, might be a bit more. Can you calculate if that matches? So basically, we group by the data based on unique values in the column based on which we group by. You probably need to do this a few times in the exercises to grasp it. What was the result?
612.
612, okay. Yeah, so it's roughly, we had the 51 unique years, and then 1 year has 12 months. So 51 times 12 would be 612. So we have, all the years don't have a complete record based on this information. Okay, so I'll just go ahead and modify my code. I now grouped based on this year month, which has the details. I could also do grouping based on 2 different columns. So we have the separate columns year and month. I'll put those inside a list. It doesn't matter which approach you use, but I think we have this in the lesson materials. Okay, so now I have group by list of 2 columns. So then it looks at unique combinations of those columns, and I should get the same result here. So we have 601 groups at this point. Again, we could print out the group names, so group keys at this point. There's only 601, but I won't do it here. You can try it if you want. But basically we could then, now we have grouped the data, so we can start looking at the data per group. For that, I'll just define one group name. I think this should work, let's hope so. So let's look at April 2019. I create a variable for data from that group. And this pandas data frame group by object has a method called getGroup. And let's see if this works. At least I don't get any error. Group 1. I'll just print that out. Okay, so what happened in here is I define one, because I grouped the data based on year and month, right? So the name of the group is a combination of the year and month. And then from the grouped object, I get the group for year 2019, month 4, so April of this year, and then store that in a variable, and as an output I get a data frame. I might as well just print out the head to get less data. So you see that all these timestamps are from April 2019. If this went too fast, maybe you can raise your hand and somebody can help you. But to reiterate the point, when we group data, we kind of create these mini data frames for each group. So for each unique combination or each unique value of the column we grouped by. And then we can access the groups and apply pandas functions on those groups. All right. And indeed, still I can check group 1. So I have this data frame, then group 1. So now I have 2,000 something observations for April 2019. And then you can imagine I could take, for example, the average of these values. Was everybody able to group the data? Was there any problems?
I'm getting
Yeah.
a key error. And
Yeah.
it says my key error is from 2019.
Okay, so it depends then, because I kind of did a quick switch. So are you grouping by year, month, or list of year and month?
The first.
Yeah, so if you change your code like this, then the year, month, what you have now should work. So it depends, the keys depend on the by parameter. Any other problems? Emil, did you have something?
Yeah, I have the same.
Yeah? If you check here, if you change your code like this,
Yeah.
I went a bit quickly there. Works. Okay. So, in the interest of time, I'll skip over some of these things. Now we are at, okay, so we were here, we checked that we have one group, that's a data frame. Here we have instructions for calculating mean over several columns. I hope this is not confusing. I'll kind of take a shortcut so you can just watch what I'm doing. We'll soon do the same thing for all the values, but we had this group 1, which is now data for April 2019, and if I would take then from there column temp C and calculate the mean, so I get 5.8 Celsius degrees. That kind of makes sense, right? So now we have calculated mean for April 2019 out of all, like, picked that out from all these rows of data and calculated the mean. Makes sense? And then of course we would want to do that for each April in the record, right? So I'll go ahead and skip this step. The point here was to calculate mean for multiple columns, but actually for this April task we only need the temp Celsius, so I'll just skip that now. But the more important thing to check is now here under the title for loops and grouped objects. So we'll go and see how we can then calculate mean for each group in the data, and each group in the data is now each month. We haven't yet kind of taken out the Aprils, but we'll do that soon. So in the same way that we did with this iter rows, when we do a for loop with a grouped object, so we'll get the key and the group in the grouped object. This is again a bit different than the basic for loop, for example with lists. The group object contains information on the name of the group, so in this case the combination of year and month, and then the group is the actual data, so the data frame for that month. And if I print this, again only for the first round I get the key, which is 1906, and then 1, so January 1906, and then these would be the values for January 1906, right? Okay, so all you had to type in was this for loop syntax, so for key, comma, group in grouped, colon, and then run. We just print out the value of the key and then head of the group. Okay. Once again, you'll practice this in the exercises to understand it better. So finally, if we would want to calculate the mean for all the years, I don't actually know if we have time for this, but maybe, yeah. We should, yes. So let's walk through the process of then actually getting the mean value for each group and then storing that in a new data frame. In principle, we'll have something, for example, called monthly data, as we are grouping by months. And let's just make an empty data frame for that. pd.data frame, like this. So that will be our output. And then here, I skipped this step for the individual group, but we'll now do that for all the groups. So I define a list of columns for which we want to calculate the mean. We'll get some extra information also about the speed, wind speed and such in this case. Then again the for loop. So for key group in grouped. I think this comment is a bit off, but basically we want to calculate the mean for each group. So we would do something like mean values equals group, and then we'll get at this step mean calls. So what happens here is that we have the data frame for that one group, and we select only these columns, which makes sense for taking an average of, and then using a pandas data frame function, we take mean value for all those columns in that group and store those in a variable. Yeah, we can do this, so we can then store the information also about the group name we are dealing with. So we'll add a new column called year, month equals the key. So for each round, the key is related to a new year-month combination. And then finally, monthly data equals so in this case, we'll append, we have an empty data frame, like we could have an empty list, and then we'll append the information into that object. And then there's a little trick in order to avoid some error messages. We'll add a parameter ignore index equals true. Maybe we don't stop and explain that too much. I'll just try and run this and let's see what happens. I think this was previously done for hourly data, so monthly data, there we go. Okay, so then you see that on each row there is a unique combination of year and month, so January, February, March, April, so on and so forth for each year. And then there are mean values for these different columns that we gave. Okay, somewhat clear. Any questions? Mm-hmm. Yeah. You might, yeah.
Can you scroll a bit up?
Sure.
I'm not gonna be referring to the group, but we defined so many times the group.
Yes, sorry
What
about
do you have
that.
it now?
So, yeah, in principle it doesn't matter which version you have, but my version now looks like this. Yeah, it's maybe easier to understand what happens if you only have one column in the by parameter, but this gives the same result, so it looks at unique combinations of those two columns. Okay? Okie-do. So we're almost there, maybe a bit behind schedule, but let's not worry about that. This is also something you might need to read through, kind of read it row by row, think about how the for loop goes through the data, takes a mean, adds it to the output data frame, so then we end up with these mean values for each month. Does Dave have a comment yet or soon? Yeah. Okay, so as I said, we're almost there. I'll just kind of push through the end in here. Of course, now that we learned this very complicated for loop thing, you could also run grouped.mean and actually achieve kind of the same results. Again, here, sometimes you need to do things with the for loop if you want to do more complicated things. If you just want to run some of these very basic statistics, such as minimum, maximum for each group, you can use this syntax as well. Mm-hmm. Okay, yeah, so we have kind of, well, quite a lot still to do, but not so much in terms of the whole analysis process. So finally, we have converted temperatures into Celsius, we have extracted information on the month, so now we should be able to calculate the mean temperatures for each April and see if indeed April 2019 was warmest on the record. So I'll just go ahead and type these in here. Now for this one station. So let's select April's equals data. We learned this, was it last week? So if we want to do a selection based on a column, so we give data. We have the column called month equals 4 is April, I guess. That should work. So this gives a series of true-false values, and then it takes all the rows that are true based on the condition inside the outer brackets and stores them in there. April's head. So indeed, I think I see some observations for the month of April for the first year in here. So should be correct. Then I'll group, well, first I select some columns from there. Then we do the same thing as previously, so grouped equals April's dot group by, and then by, I'll now use this list of year and month. To get a grouped object for only rows that contain information for all the Aprils. And then here I can use the one-liner. I'll stop soon to pause. So we can calculate grouped mean. Oops. Okay, so that starts to look quite nice. We have April for each year, and then we have some mean values in there. I'll go ahead and store this in a variable, so monthly mean equals grouped mean, and scroll up a bit in case you weren't. Did everybody get this? Data equals 4. So we first get the Aprils sliced out from data, then we select some columns, and then we group by year and month. So the same thing as there. And then we get the monthly mean. Monthly mean values, monthly mean head. Looking at Dave because we still have quite a lot of material for you, but let's see how far we get. So far so good. So this already starts to look quite useful. Then how could we get the warmest Aprils on record for this station? Well, a very simple approach is just to sort the data from highest to lowest. We could of course take a maximum, but we might want to compare, like see the top 5 warmest. So now we have this monthly mean data frame with the grouped means. Then we learned last week this sort values. We want to sort by temp Celsius, because that's the temperature values we are able to understand. I could first run this one, but you see that the sort values by default ranks ascending, so from smallest to largest, so we need to set ascending as false. Okay, so surprise, surprise, 2019 actually is the warmest April on record, at least for, are we now in Tampere? Ta-da! So at least the headlines are correct for Tampere. You can of course also treat if you just want to have the top 5 results sorted in a descending order. So there we go. Okay. Is there any questions about this? So what we did, we converted temperatures, we grouped the data, first we extracted the relevant level of detail in terms of the timestamp, and then we grouped the data. We threw out everything else except for months of April, then we grouped based on April, so average over each month of April ranked, and here we have the top 5 hottest. Well, 6 degrees is not so hot, but it's still for April temperatures. It was at least the warmest on record. Okay, so we are almost at the end, except that we have a big bunch of code in the following code cells. So just to remind you about what we did, we have put all these different steps into one code cell. So often maybe these types of things you might write in a script file and just run everything at once. So now if you just run that thing, we'll get some errors. Oh yeah, aha, yeah, I demonstrated some file path stuff during the break, so that's why it breaks. Never deviate from the script. Where do we have the file path? I'll just rerun. So don't do what I'm doing now. No. Yeah, everything falls apart at this point. Okay, I rerun, so the file path needs to be correct. But then if I rerun this big code cell, we also added some nice print statements there. So station number, number of observations, and then the warmest Aprils on record. Let's just go ahead and show the globe, and then you'll have 15 minutes. Okay, did you manage to run this? Even if you would have kind of fell behind at some point, all these codes in here should work. So indeed, we read in the data, we rename the columns, we print out some information based on the column, the station number. Then we calculate the temperature here using the function apply method for applying the function. In this code block, we use the string slicing for, I don't know, for some reason it's actually faster than converting to date time. So just to speed things up, we have the month and year columns, we extract April, we take some subset of the columns, group by year and month, take the mean, print the sorted values. Okay, that's cool, but we also have these 15 other stations in there, so we should like that repeat all of this for the other 15 stations. So at this point you might start thinking that if you would be doing this in Excel, you would then have to reopen, or unless you're skilled with Excel macros, so you should reopen the data, do all these steps, and there's all these different manual possibilities for manual error. So here we are actually getting to the good stuff in a way. Maybe, I don't know if Dave looked at this view, but you indeed have all the data files in this lesson 6 data folder. I have here 4 stations, some of you might have more, and then these files are metadata. So what we should do is to list the input files and then loop over the input files and repeat the process. We'll pretty much kind of show here how it's done, as we don't have so much time, but there's a little handy module called glob, which we can use to list files in directories. So we'll import that, and then we'll want to create a list of files. File list equals, and then we'll use from the module glob method glob, not blob, like this. There's different ways of doing this, but in principle we need to give the directory path to glob. Somebody asked during the break about this R. In short, it reads in the string as raw format. You remember that, for example, if we have -n, that creates a new line. So if you would be called Nina and you have a folder -Nina-data, then your file path will actually break where there's this -n. So that's why we have the R here. In short, the data is located in data folder. In this case, the R doesn't actually help us. But anyway, and then in addition, as we had these other files, so these are metadata files. These 4 are actually containing the actual weather observations. So we can provide a pattern to glob to list all the files that match this pattern. So they are all txt files extension, but they also all end with 0. And then we can have this star. No, is that correct?
I did 0 star.
0 star.
Because they all start with 0 as well.
That's true. Well, yeah, actually it doesn't matter. We can do that. 0 star. The basic thing is that we need to provide a pattern for glob to search for files, and whatever is marked with star can be anything, as long as it starts with a 0, something, 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 and ends with txt. So let's see what we get. We can print the file list. So if the syntax is correct, we should have a list with all the available input file names, right? And we can loop over that list for fp in file list, print file path. I know this goes a bit quickly, but we can then discuss it later. And then finally, as we had this big code block of lines for doing all the processing, we just indent all of that, put it inside a for loop, and repeat the process for each input file. So fingers crossed. I'll just go ahead and run that. And if you manage to use glob correctly, you should see results appearing for each input file that we have in the folder. Does it work? Yeah? Cool. Yeah. And of course, then from here we could start doing fancy visualizations, calculate better statistics and such. But it's always a good idea to develop your process with, well, not with 75,000 rows of data, maybe even a smaller subset of the data, and then repeat the process for data with similar structure. And then now finally, we can check how did April 2019 rank. Now we have 4 stations in here. On the website you have 15 different stations, and the station names are indeed available in these metadata files. So for station, I think this was Marienhamn in Holland, 700, because I checked it this morning. So there, 2019 April is only the 4th warmest on record, so since 100 years. But still, here it's top number 1, top 2. So not in each station, but pretty much April 2019 was one of the 4 warmest Aprils on record to date. End of story. So if you have any questions, let's discuss now or after the lesson. But do you have some burning? Did everybody manage to do this glob thing? So the point is to list files in a directory so that we can loop over a list of file paths to repeat a process. Yeah, okay. So that's it. You have all these materials on the website, so you can repeat them. Now we still have some time for, something that Dave wants to show us. Thanks.
Yeah, okay. So I've had the luxury of sitting up here looking at you guys sort of gradually getting lower and lower in terms of the energy. So I'm not going to kind of overload you with a bunch more stuff because I can kind of tell the saturation point is near. What I will do is show you a couple other things that are on the course page for the lesson for this week that could be of interest to you, and then talk about the exercise briefly and leave it at that. Because as much as I enjoy talking about stuff, I think at this point I would be more or less talking to myself, and that's not really that appealing. So just going back to the lesson page for a second, there are 3 other things we have not covered. They are far shorter than the topics that we've dealt with so far with this Pandas lesson. That was clearly the kind of big thing for this week. But there is some material here about dealing with error messages. And really the essence of this is just to remind you of a few of the common types of error messages that you will encounter, and also make note of the fact that when Python gives you an error message, there is an attempt to try to provide you with some useful information that will help you solve the problem that led to that message being produced. So there's an example here, for instance, of assigning a wind speed of 50 kilometers an hour, then converting that wind speed to meters per second. And in this case, leaving off a quotation mark at the end of the line that leads to a syntax error. And then you can see underneath here in the little annotated figure here, showing basically the same error message and the information that's presented to you when that error message occurs. Most of the time, I'm guessing you guys see this big pink box and you're just like, ugh, I've got some problem. And like, I get the feeling that, of course, when you get like dozens of lines of stuff dumped to the screen, it's a bit overwhelming. But typically, most of the information you're looking for will be in the last line or the last 2 lines of that error message, including things like the type of error that occurred. If you get something weird, you might just put that error message into Google and see like what does that actually mean. And then there's some more information here. This error message itself, I think I showed just because it is kind of a nasty one. This EOL while scanning string literal doesn't mean a lot to many people, but EOL in this case is end of line, and what it was trying to do was read through some character string text, and it encountered the end of the line before encountering the quotation mark that should be there at the end of the line. That probably by itself doesn't tell you a great deal, but there is this little caret or upside down V-shaped character here that does show you the location where the error message occurred, or where the error occurred on that line. And that actually could be useful, because if you look for where that thing is, it'll usually be in the line that's beneath the line of the code that caused the problem, and it tries to show you as best as Python can guess where the problem occurred. If you take a look at the information that's here and you just sort of take a breath first before feeling upset about getting the error message, there is quite a bit of information here, and if you take your time and just read through it, you will find that this information can help you solve problems pretty quickly. There are going to be cases where you get a really nasty error message, and it might be something that's challenging to deal with, and still for all of us that do this kind of coding regularly, that still happens. But for most of the cases here, like in the exercises that we're working on, typically you'll see error messages that point you pretty efficiently to the place where you should go make a change in your code. So there's more information about the error messages that you can find in that part of the lesson, some examples of different kinds of error messages and things like that that you may want to just read through. Our good coding practice for this week is about using assertions. I'm not going to go through this in any detail, but basically assertions are little tests that you can insert into your code to make sure that the code is doing something meaningful or using meaningful values. So the example that's given here, again, is defining a function to convert wind speed from kilometers per hour to meters per second. And one thing here that we go over is that we might assert or have a condition that says that the value for the wind speed should be a positive number. Wind speed will always be the magnitude of some velocity, so it should either be 0 or some positive value. It should never be negative. There's no negative speed. So we can basically build something into our function that says, for instance here, assert that speed has to be greater than or equal to 0. If then someone using the function, even yourself, puts in some negative value, you would get an error message that would pop up that would tell you something like, as you can see here in the later example, that there's an assertion error, wind speed values must be positive or 0. So these are little things you can build into the code to make sure that your function is being used the right way and that it's going to not perhaps produce some erroneous results. Of course, you can convert a negative wind speed from kilometers per hour to meters per second, but you may want to just have a test in there that says, okay, well, it doesn't make any sense to use a negative wind speed, because if you then later in your code assume that the wind speed value is positive and do some other calculations, you may encounter trouble down the line. So there's lots of different ways in which you can use assertions to check the values. The example that we give here of a second case is to assert that the wind speed is not only positive, but that it's less than the maximum wind speed that's ever been measured on the planet. So that's also just to sort of check, is this a reasonable value? And so you can see some information about using assertions there. Again, I would encourage you to read through the lesson there. And finally, there's something here about debugging your Python code. It's more or less just a bunch of text with some tips about how to debug code. It would not be very interesting for us to discuss here, but this is just basically some strategies that when you're getting into now writing a little bit more complicated code in your Jupyter notebooks, how you can go about solving code problems efficiently. So if we turn then now our attention here to exercise number 6, we can see here the kind of overview of the exercise. We're doing data analysis once again with pandas, and in this case we are again using some data from the NOAA. We have in our data file several different columns. They should look pretty familiar because many of them we have already seen. And you're asked then to basically do 3 problems for which you will be assessed. And then there is, again, a bonus extra optional problem number 4. For problems 1 through 3, they are all in one notebook, and this is because rather than having you reread the data file several times, we can read it once in the notebook and then proceed on through doing the analysis here. We're doing the analysis, of course, in a couple different steps, and it's useful just to have already read the data file once so that whatever you've done in terms of earlier processing is available in problem 2, for instance. Our data file in this case is a slightly different format than what we had before, and if you open it, let's see here, if it lets me see this. Oh boy, that is pretty small. Let's see if I can make this bigger. So what we're dealing with here in our tricky data format is the fact that we have some identifiers up here in the first row of the data file, but then there's a row of these dashes here that are separating things. So now we get to deal with reality. Once again, this is a data file that was just downloaded directly from a data source, hasn't really been processed in any meaningful way other than maybe we trimmed off some lines to keep it manageable size-wise. But we've got a new challenge, and that is skipping over the second row. So that's the first problem, essentially, is dealing with skipping over a row in the data file and then reading it in and converting some -9999 values to not a number, because that's the designation for not a number in this particular data file format. After you do that, then there's just a series of little questions about like how many data values do you have, and doing some kind of basic processing of the data file just to get a sense of what you're working with. What's the earliest date of the data that we have here? It's again temperature data. What's the most recent value? Things like that. Most recent observation. Problem 2 involves calculating monthly average temperatures. This should probably also sound somewhat familiar, but this is our data aggregation problem, where I think in our case we are dealing with observations for, I think more frequently, maybe these are daily values. I don't remember whether they're daily or hourly in this data file. I think they're daily values. And you're going to be then calculating average temperatures for each month rather than having average temperatures for each day. So you'll go through more or less the same process that we followed during the lesson of doing a little bit of conversion from Fahrenheit to Celsius and then averaging the values to get a monthly average temperature. And I think in essence that's pretty much what you'll do for problem number 2. It's not really something where it's sort of complicated in terms of the description, but it'll take you a little bit of code to get that to work. And again, then once you've got that working, there's a few sort of little print statements that you'll see to give you a sense of what the data look like. Now, problem number 3 is doing something slightly different, and that is to calculate temperature anomalies. So when we start looking at climate data, we want to look at trends in climate data. Something you might want to see is like, is this year or are the temperatures for this month warmer than average or colder than average? And so in order to do that, you have to know first off what is the average value in order to be able to calculate whether you're warmer or colder than that average. So problem number 3 will involve calculating average temperatures for some reference time. So what we're going to do for each month, January for instance, is say what's the average temperature in January from 1952 to 1980. That's the reference period that's often used when looking at things like changes in climate over time. We calculate the average temperature over that time window, and then once you have that average temperature for that time window, you can then take a given January for a certain year and say how different is the temperature in that January from the average. So just to reiterate, if we calculate average from 1952 to 1980, that will give us some temperature value. And then we could go to a given year like 1996 and say, okay, in 1996, if we take the difference between our average for January and the actual temperature for January of 1996, we should see whether that's warmer or colder than the value for the reference time period. So this is a little bit different because we're going to take a bunch of years over some time period and calculate then like what the average temperature is. So what you should see for January between 1952 and 1980 is that the average temperature was minus 5.83, blah, blah, blah. You'll do that for all the months, and then once you have those values, you can calculate how each month of each year differs from the sort of longer term average. This will set us up nicely then for our lesson next week when we start into plotting, because we'll then be able to do things like plot these temperature anomalies, which kind of brings us back to the first lesson when we had our little introduction and motivation for the course about visualizing data. So that should hopefully kind of tie things all nicely together at the end. You have any questions? Okay. If not, thanks for bearing with us. I know today's lesson was a bit heavy. It always is. And we'll see you in the exercise sessions.